everyone, welcome to my channel. What if AI could help doctors detect and segment brain tumors in seconds? In this video, we are diving into the cutting edge of medical imaging using YOLO11 for fast tumor detection and SAM2 meta segment anything model to accurately outline the tumor region pixel by pixel. We will walk through how to combine these two powerful models for brain tumor segmentation and show you real results on real dataset. Whatever you are a student, a researcher, or just curious about AI in healthcare, you are in the right place. Let's jump in. So we are using this dataset from roboflow.com. You can easily download it as a zip file. You have to select it YOLO11. Here we can see that in train set there are 1370 images. In valid set there are 395 images. In test set and there are 191 images. I have already downloaded. So here is my folder. I will use a Jupyter notebook. Click here and write CMD. Then write a Jupyter notebook. This will open your Jupyter notebook in this folder. I have already created a Jupyter notebook, so I will explain this notebook for your better understand. In my training folder, you can see that there are different types of images. So let's dive into the code. Here we are using Ultralytics module to perform YOLO. For this, simply write install Ultralytics. This will install Ultralytics in this Jupyter notebook. So I have already installed it. So it's so that requirement already satisfied. So from Ultralytics import YOLO. This imports the YOLO class from the Ultralytics package. The Ultralytics YOLO library is a user-friendly API for training, validating, and running inference with YOLO models. Here model is equal to YOLO11 n.pt. This line leads a pre-trained YOLO model named YOLO11 n.pt. This line loads a pre-trained YOLO model named YOLO11 n.pd, where n means nano. YOLO11.pd is likely a custom or fine-tuned model file. The naming resembles YOLO v8n.pd, where n means nano, the smallest model. If YOLO11n.pd is a typo or renamed, make sure the model exists in your working directory. This becomes the best model which you will fine-tune on your custom dataset. This line initiates the training process with the following configuration. Data is equal to data.yaml. Here you can see that in my folder I have downloaded from RoboFlow. There is a data.yaml. This is the path to a YAML file that defines your dataset structure. YOLO uses this file to understand how to load and label your data. This is showing our directories path. Nc is equal to 5 represents the level. Here there is 5 level: no tumor, glioma, meningioma, pituitary, space occupying lesion. Next, apex is equal to 20. It specifies the number of training iterations. One apex is equal to the model sees wall training image once. More apex typically result in better learning. Here, image Z, wall input images will be resized to 640 into 640 pixels during training. YOLO models are optimized for 640 cross 640 by default, but this can be adjusted. At device is equal to CPU. It specifies to run training on the CPU. If you have a GPU, you can use device.CUDA for much better training. So I have already run this coded and run some iterations, 20 iterations, and here is the result. And that's how I train my model. Then what happened if you run this code? The YOLO model loads the YOLO11n.pd. It reads the dataset details from data.yml. Then it starts training for 20 epochs using resized 640 into 640 images. Training runs on the CPU and returns results like loss matrix, classification, localization, objectness, accuracy, mean average precision, trained weights saved in the specific folder. After training, you will find trained model weights base.pd, last.pd. After running this code, we will see that a runs folder. In this runs folder, we can see detect folder and train folder. In this train folder, we can see that levels.jpg, levels choreogram.jp, train base, and some train bases. In this train2 folder, you can see that weights folder. In this weights folder, you will see that base.pd and last.pd. This is the main base.pd, and we can use this. We will use this base.pd to perform the model. So here we import YOLO classes from our analytics model, and then images and display from the IPython.display, used to show images directly inside a Jupyter notebook. OS Python module for file path manipulation. In this line, we will load a custom trained YOLO model from the given path. Base.pd is the best performed model, saved during automatically training. Train2 is a folder generated by YOLO during training. In this line, runs detection on the specified image. Save is equal to true tells YOLO to save the output images automatically. Results is a list of results object on per image. In this code, the folder where the annotated image is stored, results.path, original image path used to get the file name, builds the full path of the saved result images. This shows the saved annotated images within your Jupyter notebook, so you can visually verify the object detection results. What you can get: bounding boxes drawn on the images for detected objects, display of the annotated result right inside your notebook, saved image in the specific path or directory. So here we can see that we have successfully detected meningioma tumor in this picture. We are using this image named meningioma. So here my model is perfectly predicted the same result. I have tried another image named no tumor. So my model predicted no tumor. Here 0.9 mean accuracy. So it is shows that it is more accurate result, perfectly predicted. Again, we uses another image that is named pituitary. So my model perfectly predicted a pituitary tumor. In this line, it loads the custom trained YOLO11 model. The file base.pd is the model checkpoint that performed base during training. Result.model test images set true. Instead of passing a single file, we are passing a directory. YOLO will run inference on all images in that folder. Save true tells YOLO to Annotate the images with bounding boxes. Save them in a new folder, typically named something like predict2, predict3, predict4, etc. If rerun multiple times. So let's run this. So specifically, this line will perform prediction on a specific folder. So I have a folder that I created. It's named test images. In this folder, I have passed some picture. My model will perform predictions in all those images without passing through images one by one. We can use folder directly to predict all the images inside the folder. So here my model predicted test images 1 as pituitary, meningioma images as classes on meningioma, then meningioma images as on meningioma perfectly. No tumor images predict no tumor. Pituitary images, for pituitary images it is predicting pituitary, and then again for pituitary images it will predict 2 pituitaries, and these all files saved to runs detect predict 4. So let's go to the folder. So in this folder we can see all the predicted images, and you can see that my models predict pituitary perfectly, then meningioma tumor perfectly, then again meningioma accuracy 94, no tumor accuracy 90, pituitary 82, and then it predict another, but its accuracy is 47. So 82 is more accurate, so it is predicting pituitary. Then again pituitary with accuracy 89. So we can see the process result list with this code. We are iterating our each result in this code. We are iterating our each result in the results list returning from the YOLO's inference. Result.boxes gives us a boxes object which holds coordinates of detected bounding box, class levels, confidence scores. After run this code, we will see that in this line we are passing pituitary images in this model. So my model shows the path, and then resolution. YOLO resized it to 640 into 640 during inference, and this is my model detections. It found one object with the level pituitary, and inference time 418.7 ms, which is decent for CPU. CLS tensor 3, this the class ID of the detection. If you have a class list, ID 3 maps to pituitary. Tensor 3 means it predict the class 3 means pituitary. Class 1 means glioma, class 2 means meningioma, class 3 means pituitary. So my model shows class 3. This is a confidence score. My model shows the confidence score is 89. That is a very good score. Data bounding box combines all x1, y1, x2, y2 confidence and classes. x1, y1, x2, y2 confidence score, and then class title. Here is struct is ball. Original shape is 640, 640. Here shape toss size 1,6. 1 means detection and 6 means attributes per detection. Here this is x center Y center, width and height. XYWHN, normalized version of XY. All values between 0 and 1 used for consistency across resolutions. In this code, we import as usual YOLO and SAM from Ultralytics module. This line loads our customer trained tumor detection model. It's been fine-tuned likely on a brain tumor dataset. We are detecting tumors in a single images using YOLO. Results is a list of results object on per images. This line loads a pre-trained SAM model. This model segments objects based on bounding boxes. SAM2b.pd likely refers to a lightweight or modified version. Here, loop through YOLO results and segment with SAM. Extract the list of classes ID 3 for pituitary, 0 for no tumor. I have said it. We passes original images plus YOLO bounding boxes into the SAM. SAM then outputs precise marks around the detected regions. Save2 saves the segmented result to the disk. YOLO detects rough location of the tumors and refines this into an accurate segmentation mark. We can get high quality localized segmentation even with a small irregular shape. Here you can see that detection one object detected and the classes meningioma. Results saved to segment folder, then predict to folder. Let's go to the segment folder and then predict to folder. Here we can see that my SAM model is given marks to the YOLO11's predicted images. YOLO11 just created a box to the predicted tumor images around them, and the SAM model gives a marks to the result of the YOLO11 predicted images. So this is how we can use YOLO11 and SAM2 model to predict tumor. So that's all guys. Thanks for watching.